All right. Hello, everyone. My name is Dr. Tejas Puranik, and I'm a research faculty member at the Aerospace Systems Design Lab at Georgia Tech. I'm going to be presenting our work on deep spatio-temporal neural networks for risk prediction and decision support in aviation operations that has been conducted in collaboration with graduate student Yoonki Lee and lab director Professor Dimitri Mavris. I want to take this opportunity to thank Dr. Gupta and the journal team for inviting us for this Spotlight Talk series to give our presentation based on our accepted paper in the journal. I've indicated the link of and the full name of the paper at the bottom here in case anyone is interested to read the paper. So I'll get started. A quick outline of my talk for today. I'll give a little bit of background and motivation context for the work we were doing in this paper. I'll follow that up with the methodology that we used for analyzing the data, developing models, and so forth. Following that, I'll dive a little bit into some of the results we obtained from our analysis, including predictions from our prediction model, as well as safety score from our prediction models. And finally, I will conclude with some concluding remarks and avenues of future work. So to start first with the background and motivation, one of the key components of modernization of next generation aviation systems is a transition from radar-based operations to satellite-based navigation and surveillance. What that essentially entails is a requirement for accurate flight trajectory prediction, as that would be needed to avoid accidents and reduce errors to ensure safety and efficiency. Trajectory prediction algorithms are a very crucial component of decision support tools that are used for a number of purposes, such as conflict detection and resolution, arrival metering, and other air traffic management applications. In particular, the approach and landing phases of flight are identified as some of the most critical phases of flight from the perspective of safety of operations. An example of an accident from 2005 is shown here on the right, where the aircraft landed on a runway that was contaminated at a high speed and resulted in a runway overrun, which resulted in the loss of one person. So we want to try and avoid accidents and incidents as far as possible, and providing a reliable prediction of risky situations of the future is valuable for online condition monitoring and decision support, particularly during these critical phases of flight. If an approach is considered or deemed to be unsafe to continue the landing for whatever reason, one of the options that a pilot has is to perform what is known as a go-around maneuver, where the pilots and the crew attempt to perform the landing once again in order to avoid the risk of accidents like runway excursions or controlled flight into terrain. So overall, an accurate data-driven prediction of the aircraft's future state and potential risk is critical to decision-making in these phases of flight. So with that background and context, the objective of this particular work was to try and demonstrate some novel deep learning model applications for online prediction of future aircraft trajectory states and safety score during the approach phase. I'm going to talk more specifics about what this means in some of the upcoming slides. But really, two important things to note here is we are interested in looking at an automated safety score prediction and generation of model for online applications based on data or flight data that has been collected from routine operations during the approach phase. And then secondly, we want to make sure that this prediction of risk gives air crews enough time interval to take some kind of preventive action. So we want to try and build a system that can provide enough advance warning for the pilots and air crews. So with that sort of background and context in place, I'm now going to talk or dive into the methodology that we developed for tackling this problem and how we implemented this method. So overall, I'm going to talk about a description of the method along with the flight data that is used for training the models and validating the approach. I'm going to spend a little bit of time explaining our model setup, specifically the way the spatial and temporal features of flight data and flight dynamics are used, and then touch a little bit upon hyperparameter optimization that was conducted for this work in order to get the best possible models for this problem. So in this slide, I have a sort of a big picture overview of the method that we developed for this work. We've sort of divided it up into two main parts. The one above the dashed line here is the offline model generation and validation part. And the one on the bottom is what would be ideally deployed in an online context to help with the decision making. So we start with the flight data, which I'm going to be talking about on the next slide. Pre-process, clean that flight data, divide it up into training, validation, and test sets, as is typical of any machine learning model application. We identified certain baseline models that are suitable for this kind of spatio-temporal problem in the literature, and implemented some of those in this work. Then we go into the hyperparameter optimization to really nail down the best possible architectures given those baseline models. And then the chosen model gets deployed on the test data, which is not seen any of those model training and validation exercises, in order to provide those prediction metrics, identify significant parameters, and give the air crews and air traffic management personnel an overall decision-making information. So this is this is how the method is set up overall. Now I'm going to dive a little deeper into some of the components of the method and how we built those. So starting first with the flight data, what we used in this work is called Flight Operations Quality Assurance data, or FOQA data. This data consists of thousands of parameters that are recorded, could be recorded anywhere between 0.25 to 16 hertz frequency. The data types could be numerical, discrete, binary, or text-based, or nominal. And this data is typically organized as a hierarchical structure of flight data parameters. So at the very high level, you would have umbrella terms like atmospheric, engine, altitude, control. And then as you drill deeper into these high-level categories, you have subcategories, and then the individual parameters that are recorded. So for each vertical, there could be multiple end states. For example, thrust could be recorded in different units. It could be corrected thrust, uncorrected thrust, and so on and so forth. So this sort of hierarchical structure of flight data parameters is available for this work, and is typically available for commercial airline operations. The data file that we receive from the FOQA data for each flight is flattened and processed so that we have a single row, which is typically called the feature vector in machine learning applications, is created, and it includes all the data from the time steps of the flight phase of interest. So I'm going to talk about how we choose the flight phase of interest and other things in some of the following slides. Finally, there needs to be some level of pre-processing that needs to be done on this data that includes, but is not limited to, identification of the phase of flight, removing parameters that are not usable for this effort, and some other standard data cleaning protocols such as imputation, filling, parameter removal, and so on. So after this pre-processing is complete, we end up with a slightly shorter list of parameters, but those that are more directly usable for this type of work. So now I'm going to talk about how we have set up the model, and this is really sort of the important aspect of how we are setting up the model to provide the predictions of metrics of interest. So To start off, we have data that gets collected between critical altitude gates or decision gates. So the picture on the left here shows two parameters, the height above touchdown and the ground speed of an aircraft as it is coming into approach and land on a runway. So the solid line indicates the past track of the historical track of the aircraft, and then the dotted or dashed line indicates what happened after the point of interest. And so the data that we are going to use for the prediction model is going to be collected between the critical decision gates of 1,000 feet above touchdown and 300 feet above touchdown. The reason we are selecting these two altitude gates is because during approach and landing operations, a lot of decision making is typically performed based on altitude rather than the distance or time remaining to touchdown. And so these two are gates where the pilots might evaluate whether they are on the right track, whether there needs to be any corrective action, and whether a go-around maneuver might need to be executed because the landing might not be possible. So the data between these two gates is collected to be fed into the machine learning model. The data sets that we are looking at have around 170 plus parameters on which the pre-processing and reduction gets completed, and then it gets passed on to the more standard steps of a machine learning model pipeline. Something to note here is, the structure and setup of the model specifically relates to the spatio-temporal aspect of flight operations. So the reason for that is, analysis of flight requires the understanding of, both long-term and short-term behaviors of the aircraft dynamics. The effect of things such as control surface deflections, etc., can have an impact on the trajectory of the aircraft at any point in time. And this is specific. This is the temporal aspect. But then, as I said earlier, due to the highly procedural nature of operations, especially close to the terminal airspace or close to the runway and the airport, there are a lot of spatial considerations as well that relate to how the aircraft is positioned with respect to the runway and other considerations, which can mean that the same types of control actions might not be possible or might not lead to the same types of severe or non-severe effects on the aircraft's trajectory. So this is why setting up the model in a certain way is desired. Once the reshaped feature vectors are passed on to the model, the metric for prediction is selected. In this case, we select ground speed as a metric for prediction, which is a very important metric from the perspective of runway overruns. And so the future trajectory states are then predicted at 50 feet altitude increments or decrements. So, we stop collecting the data at 300 feet and then make a prediction for 200, 150, 150 feet above touchdown. So those are the 4 future trajectory states that we are looking at. Just a little bit of information about the baseline models and hyperparameter optimization. I won't go into too much detail here because we've left that for the paper itself. But we explored 2 main model types for the deep learning models. Those were LSTM models and a combination of convolutional or CNN and LSTM layers. The number of layers and other aspects such as dropout and other hyperparameters were varied during the hyperparameter optimization. But these 2 baseline models were chosen because of their demonstrated ability in literature to handle spatial and spatio-temporal and temporal aspects of the data that is fed into those models. For hyperparameter optimization, we went with an algorithm called Hyperband. This algorithm combines random search and successive halving to search for the optimal hyperparameter configuration. Notional picture is shown at the top here. One of the main reasons we went for this algorithm compared to any other is that machine learning models performance is unknown. Hyperband is typically shown to perform well in a broad range of situations, and the algorithm can also handle categorical hyperparameters. So now that I've talked about sort of the overall model setup, the hyperparameter setup, I'm going to dive a little bit into the results that we obtained from training and predicting performance using our models, and then talk a little bit about some specific flights and how those safety scores and online predictions can come into play during aircraft operations. So first, I'll start with the model training and data. We used around 26,000 flights from 3 different aircraft tail numbers. So we've denoted them for sake of simplicity as tail ID 1, 2, and 3. These are all from the same aircraft type, and they're used for training, validation, and testing. We use standard splits for training and validation that are used in literature, and also used cross-validation in our framework. Something to note, the data that we have used in this work is all publicly available data that NASA has made available for aeronautics research purposes. And so that data hyperlinked here can be obtained as data for each tail can be individually obtained from the source indicated here. For each flight, as I had mentioned, there were 176 parameters, some of which were observed to be invariant and were removed from the analysis. Some of those were not applicable to the phase of flight that we were interested in, which is the approach and landing phase. So things such as takeoff configuration and things like that were parameters were removed. And then finally, the data was indexed based on the height above touchdown for 20 feet increments during the pre-processing step. This is just to make sure that in between 1,000 and 300 feet height above touchdown, different aircraft or different tail numbers might record different number of samples. This is just because the ground speeds and the true air speeds might be different for the different aircraft. And so in order to keep it consistent and in order to make sure that our feature vectors were uniform, we indexed it based on height above touchdown. So between 300 and 1,000, we were able to get that done quite easily. And then there were a number of hyperparameters that we varied, which included the number of layers, units, kernels in the convolutional and LSTM layers, as well as the proportion or the percentage of dropout in the dropout layers. And we've sort of put the full spectrum of hyperparameter evaluation range in the manuscript as well, with a snapshot shown here on the slide. Now I'm going to talk a little bit about the actual performance of the model. So from here on out, I will only be showing the results for the best hyperparameter combination that was obtained from the table or from the set that was shown on the previous slide. And so first, I'm going to talk about the prediction performance for what we call as the global model. So for the global model, what we are doing is we are using the flight data from all 3 tail numbers. So tail ID 1, 2, and 3. All of that is mixed together, and there's no differentiation between the different tail numbers. And this is done because since they are all the same aircraft type, you would expect that there wouldn't be a significant difference between the tail numbers. And so we use the mixed data for training, validation, and then the outputs of the test data are shown on this slide here, with the table as well as the distributions. So let me first talk a little bit about what we see in the table here. The top section is the absolute error in ground speed measured in knots, and then the bottom section is the relative error, which is the percentage error for the same metric. If you look across different rows, or if you go down different rows, there are different tail numbers, and then if you go across the table, you will see different altitude gates for which the prediction was made. So when I'm looking at tail ID 1, 200 feet, that means that this is the RMSE of the absolute error of ground speed for tail ID 1 across all the test flights for 200 feet height above touchdown. So the prediction was made at 300 feet, and this is how off the actual was from the predicted for 200 feet gate, and then so on and so forth. So one of the first immediate observations that we had here was, if you look down any column, there isn't a significant difference between different tail IDs, and there's no clear trend for the global model performing better or worse for one tail number compared to the other. They're all relatively close to each other. But then, as expected, if you go across a row, you'll find that the model performance steadily becomes worse, which is anticipated because the further to the right you are in this table, the further away from the prediction point you are trying to make the prediction. So you are the most accurate for predictions for 200 feet and the least accurate for predictions for 50 feet. The figures on the right also sort of try to capture the same information shown in the table, but through scatter plots. So on the x-axis, we have the predicted ground speed, and on the y-axis, we have the actual ground speed. And in an ideal scenario, you would want the entire data set to lie completely along the diagonal here. But as expected, there's bound to be some errors in our model. And so you see a sort of a little bit of a spread around the diagonal with an overall good agreement between the actual and predicted. And then as we go from 200 to 150 to 100 to 50, the spread around the diagonal increases slightly, which is also what we see in the RMSE and other errors. Now, we did perform another small experiment, which was just to see if we trained specifically on a single on data from a single tail number and tested on, again, data from the same tail number, would that make any difference? Would it make the model significantly better or not? And the results we found was that it actually did not make a lot of difference. So it ended up overfitting slightly when we were doing it just based on the tail number. And so we had, for the test data, we actually ended up with slightly worse, but very, very similar ballpark numbers for the errors observed. So that led us to stick to the global model, which included data from all tail numbers. The box plot shown here sort of also captures similar information that the scatter plots were showing in the previous slide, but now this is individually broken down for each tail number, just to sort of reiterate that point that the global model performs well overall without necessarily being biased for a particular tail number versus another. And then again, the prediction for height above touchdown, as we get closer to the ground or further away from the prediction point, the uncertainty and the error increases in our prediction, which is an anticipated trend, but visually seen from this chart here. So in this, we looked at 4 specific flights of interest, just to see what were the how did the predictions look like, and what were the actual values to get a sense for the numbers that we were obtaining from our prediction models, as well as what the aircraft had actually ended up flying in the data set. And again, the top half of this table here shows for the 4 flights 1, 2, 3, and 4, which were from spread across the 3 different tail IDs. What were the predicted ground speeds at the various altitude gates, and then what was the actual ground speed. And so you can see that in general, it's quite close, with some flights such as flight 4 having slightly worse performance than others. And so this just sort of gives us a feel for what type of numbers and what type of errors we're looking at. Now, something to note is, we are still okay with prediction errors of 5 to 10 knots, because ideally we want to flag, extreme outliers, or places where the flight crew will need to make a lot of, or will need to take a lot of corrective action. So the final step of our process was to generate what we call the safety score, which can be sort of like a single score that can be used to gauge whether a certain decision needs to be made or not. And the way we did that was on the plot on the left here, you see the plot of ground speed predicted at the 4 different gates. The solid lines in each case indicate the predicted values, and then the dotted lines indicate the actual values. And so these are the 4 flights colored by the 4 different colors shown here, along with their actual and predicted ground speeds. The way we obtained the safety score is by looking at these upper and lower percentiles of 99.5% of all the 26,000 flights, or all the training flights, and the lower percentile, which is 0.5% of all the flights. And so the way the score was calculated was by figuring out how far the prediction was from each of these bounds, and then sort of plugging it into this formulation where we can get a uniform direction for the score. So the higher the score, the better the prediction, the lower the worse. And so as you can see, the flights that have scores above 0 or close to 1 are more centrally lying, or more nominal if the band between 99.5 and 0.5 percentile is considered nominal operations. The flights that would be within that band or closer to that band would typically have higher safety scores, and then the ones that are straying far from the nominal band in terms of the predicted scores would have lower scores. And so these would be the flights that would be of interest from the perspective of assessing safety and evaluating whether a go-around needs to be conducted. So flight 2 here, which is the flight shown in blue color, is indication of a stable descent right in the middle of the band with a high safety score. And flight 4 indicates a flight that has a very high ground speed predicted, and is therefore at a risk for elevated risk of runway overrun. So that's how you would interpret and use those scores in practice. So a few concluding remarks based on what we have done and what we were able to achieve in this work. So first, we introduced a method of online risk analysis for the flights based on deep learning techniques. We demonstrated the hyperparameter optimization, so automatically generating different models and getting the optimal setup. We compared how these models were performing to similar or comparable work in terms of the root mean squared error, and sort of shown a table here at the bottom, which identifies 4 different measures of interest. So whether the root mean square score, how far in advance can you give the prediction? For us, it was fixed. What is the type of prediction, whether you're predicting a single point in the future or multiple points, and then whether you also sort of wrap all of that up into a single safety score. And so our method outperformed existing techniques in most aspects, except for one paper. However, it's noted that the high accuracy of that paper is offset to some extent by the fact that only 1 second advance prediction is available in that paper, whereas for our setup, it was between 6 and 15 seconds approximately in advance that the flight crew would get alerted. And so, this direct prediction of the parameters is a critical aspect for approach and landing phase. It can help the air crews improve their decision making as well as provide air traffic management personnel with some additional information for decision making and improving their decision making. So with that, I reached the end of my talk, and I thank you all for listening, and would be open for any other questions.
Thank you, Tejas. So I see there are, basically few attendees. If anyone attending this spotlight talk, if you have any questions, please use Q&A feature of Zoom to send your question, and I'll read it out loud. So I haven't seen any question, Tejas, but I have one quick question. Mm-hmm. So in terms of where we go from here, mm-hmm. what are the big opportunities that you see, in this line of work?
Mm-hmm. So really, there's two major opportunities. I feel one of them, I would say, is going down the path of improving in-flight prediction software. So there's there is already flight management systems and other systems on board already have some level of physics-based predictions for certain types of safety critical decisions that get made in the future. I think this can really this sort of system with a data-driven approach collected perhaps from the same aircraft or from multiple aircraft can augment that sort of flight management system or flight planning to enhance those decision making in that critical phase of flight. And then on the other side, I feel like this can also get used for air traffic management, where you're trying to maintain optimal separation. You're trying to ensure that the flow of aircraft into an airport is systematic and safe. And this is where having future predictions of states of aircraft and potential red flags that might get raised from these predictions will help reroute the aircraft that might be following it, or the aircraft that might be coming into the network, so as to make sure that any elevated levels of risk get managed and mitigated as early as possible. So I see those two as sort of the areas that we can apply this in.
Okay, so thank you very much. This concludes this spotlight presentation.
Thank you very much.